So here I'm going to talk about the next stage in the journey from planetesimals to planets, and really how these processes of planetary accretion, core formation, and internal differentiation, how they may exert some level of control on the compositions of terrestrial planet, surfaces, atmospheres, and ultimately habitability. So in the next 10 minutes, what I'd like you to do is I'd like you to look through this lens with me of planetary habitability as a consequence of planetary metal distribution. In the simplest possible of ways, what I mean by this is that the metals of a planet are distributed loosely between its core and its silicate mantle. So what we've got here are the terrestrial planets, Mercury, Venus, Earth, the Moon, and Mars. And you can see here that they've got different core to mantle ratios. The other key constraint here is that life on Earth is adapted to metal availability, specifically adapted to the availability of soluble iron, whether that's worrying about crops and fertilizer or whether that's us taking iron supplements. Life as we know it has adapted to the availability, the near surface availability of many key elements and metals. Now, if we think about a planet's oxidation state can be very simply described in terms of the balance between iron metal in its central metallic core and iron oxide in the Earth's silicate or rocky mantle. So, in other words, a very oxidized planet will have a large mantle to core fraction, and most of that planet's iron budget will be in the mantle. In contrast, a more reduced planet, Mercury is a great example of this. Most of the Mercury's iron is locked up in its core, and consequently, it's got a very large core to mantle fraction. Curiously, Mars as a planet has an even more iron oxide-rich mantle than that of the Earth, and it's actually a more volatile-rich planet than the Earth, but its mantle is actually less oxidized. And here I'm talking about the budget of iron 3+ to iron 2+, whereas in the gross planetary context, I'm talking about the budget of iron metal and iron 2+. So what we want to understand here is what controls the oxidation state of a gross planet, and then what controls the distribution of iron and other metals between its mantle and core. And the reason we care so much about these things is understanding which elements become concentrated in a planetary mantle then means that these elements become accessible to the surface. One of the key things that characterizes the Earth is this interaction between the Earth's mantle and its exterior, its hydrosphere and its atmosphere. And we want to try and understand these questions going from the very start to what controls the bulk composition of a planet, to that of its mantle, to that of its hydrosphere and atmosphere. We want to understand why the Earth is a planet that is oxidized, that can support life, whereas another planet like Mars, which in many respects is quite similar to the Earth, does not. And of course, we want to use these questions and the understanding of planetary formation that we gain from answering these questions to help us predict, hopefully, exoplanet habitability. So if we consider planetary mantle iron contents, we can get clues to planetary formation in terms of the solar system architecture and where these different planets sit. So if you might recall from Mark's talk about solar system architecture being absolutely central to a planet's formation. Basically, it dictates the material that our planet's formed from. And if we look at this very crudely, and these planets are not to scale, we can see that as we move from planets that are very proximal to our central sun, so Mercury, here we have a very small proportion of the planet's iron as iron oxide in the mantle. We go out towards Mars, we have a very iron oxide rich planet. So really what this is telling us is that planet oxidation state, very crudely in the balance of iron oxide in the mantle to iron metal in the core, is in part a function of where that planet formed in our solar system and likely the kind of material that our planets were built from. And again, this image here echoes to some degree images that Mark shown. So we've got our central sun here, and you can see here we've got Mars, Earth, Venus here. So these inner solar system planets likely formed from material that was quite reduced. In other words, a significant proportion of the iron locked up as iron metal. But they also contained material derived from the outer solar system, potentially separated off as a reservoir by Jupiter, outer solar system material, more water-rich, more oxidized. And it may be that the oxidation state and the volatile budget of different planets, so comparing, say, the Mars relative to the Earth, may be a function of this addition of material from the outer solar system. Of course, this is what you build a planet from is only part of the story. It's also what you do with it. And planetary melting and differentiation is absolutely key because it sets mantle and initial surface, oxidation state, and volatile content. So planetary-wide melting and formation of magma oceans may be triggered by planetary scale impacts such as those that Mark talked about, or very early on in our solar system, we know that planetesimals were forming in the first million years of our solar system by the decay of very short-lived isotopes. But whole-scale melting of a planet allows internal differentiation. It allows segregation into a core and a mantle. And it's the subsequent cooling and crystallization of that planet and that planet's mantle that then sets up internal mantle oxidation state, which is also key for then setting the composition of a planet's surface and that of its atmosphere. So a puzzle here that I alluded to a couple of slides ago, of course, is why the Earth, which is more proximal to the Sun than Mars, why has the Earth got an overall higher mantle oxidation state, yet a lower volatile budget compared to Mars, and presumably a smaller proportion of outer solar system material? One possibility comes from the Earth's size. And this is this unique perspective that we get from the Earth that we don't get from smaller planets such as Mars. And the large size of Earth means that we can stabilize certain high-pressure silicate mineral phases, such as bridgemanite, in which oxidized iron 3+, rusty iron partitions. And it may be that the stability of this phase in the Earth's interior in turn sets the elevated oxidation state of its mantle, oxidized above what we would expect from the position in which our planet accreted in the solar system. And understanding this is important, of course, because it's this internal mantle oxidation state that ultimately will drive the oxidation state of its initial atmosphere. So Earth's magma ocean, for example, is oxidized, and this could well then lead to an atmosphere that's predominantly consisting of water and carbon dioxide. In contrast, Mars, a smaller planet with a more reduced mantle, may have had gases in equilibrium with the initial magma ocean that were more reduced, richer in carbon monoxide and hydrogen. But of course, we know this is only part of the story. We know actually that planets can have multiple atmospheres during their differentiation and during their accretion. There's good isotope evidence, for example, that the Earth may have had more than one atmosphere. So this is my final slide, and where I want to leave things here, our take-home message is, as we know it so far, the Earth is currently the only habitable planet in our solar system. So in terms of our perspective to understand exoplanet habitability, we do have to start from the Earth, even if our ambitions are to go far beyond. We still don't know why the Earth is the only habitable planet in our solar system. Obvious other candidates, such as Venus, for example, have atmospheres that are not conducive to modern life. Processes such as the development of unique vertical plate tectonics on Earth could be potentially important, as it may allow the storage of water and other volatiles in the Earth's interior. And as Mark talked about, late delivery of volatiles, iron, phosphorus, and other metals by meteorites might also be important. And now, moving on, and with note to the next talk coming, life is adapted to abundant surface metal concentrations, abundant soluble iron 2+, for example. But it's also important to remember that this is only a comparatively recent development. I'll put recent in air quotes because that's about 2 billion years after Earth's formation. So that's about 2.5 billion years ago. But solar system-wise, comparatively recent development. in terms of oxidizing our planet's atmosphere. But this fundamental change, whilst it might make our planet habitable in the way that we know it today, may in turn have also moderated and modulated the availability of certain metals at the Earth's surface and certain metals that we depend on for life today. So thank you very much for listening.
I'm going to indulge myself and start again. So with exoplanets and the discovery of many planets on short period orbits around the host star, it may be that in the next decade, we're in the position of observing a planet in a magma ocean state, sort of trapped there perpetually by accident of its location of birth. What do you think we should be looking to learn from such magma ocean planets that we struggle to learn looking at Earth with its magma ocean epoch kind of destroyed by plate tectonics?
I would be really interested to learn about the composition of the atmosphere in equilibrium with that oxide, if that would be possible to do. I'm not an astronomer, so maybe that's not possible. But if that would be possible, I would like to learn about the composition of that atmosphere, and specifically, I would be interested in knowing its oxidation state. I think that would be incredibly powerful because we might be able to predict the planet's crude elemental abundance from the composition of the host star, but we probably can't predict its oxidation state or the oxidation state of its mantle. And I think that's where atmosphere composition would be incredibly helpful.
For those planets where we might be able to observe a magma ocean and the atmosphere, we're probably probabilistically more likely to see a super Earth. And we don't have, terrestrial planets of that size in our solar system. So, if we're basing everything on what we can observe in our solar system, how are we going to exactly understand the interior atmosphere connections on those planets? Will we need experiments?
I suppose we can use experiments to some degree to try to simulate conditions that we can't simulate on Earth. So, for example, we could simulate magma ocean conditions under conditions that are very reducing. So that technicality, that would be about iron wustite, basically about 4 to 5 log bar units of oxygen below the iron to iron oxide equilibria. We could simulate mercury, and we could do that with an atmosphere of hydrogen and argon in our experiments. So nice and safe there. So these kind of things we could do. Super Earths, we would be challenged to get to those kind of high pressures in a modern experimental apparatus. However, we do have the capacity to use experiments at lower pressure to make thermodynamic predictions that would then allow us to make predictions of mineral stability. We know a composition of a host star. We would be able to have a reasonable guess at how to extrapolate things up to higher pressures.
Yeah, so this trend of mantle redox state with the distance from the star, we can't make these observations yet, of course, but is there any way of guessing if that's going to be common for other planetary systems, and therefore could you theoretically make up like a redox habitable zone?
I think you could certainly have a go at predicting the gross planet oxidation state. So basically the amount of iron that you've got in the core versus the amount of iron oxide in a mantle. And you could make a gross approximation that you might expect that to be a heliocentric distribution. The challenge is when you get to mantle oxidation state, because that to some degree is slightly decoupled from that gross planetary oxidation state. It may be because that's due to the stability of high pressure phases on Earth. It could also be due to degassing of early reduced atmospheres, for example, or it could be due to late addition of meteoritic material, or it could be due to plate tectonics. And these are all explanations that have been proposed for the Earth. So if that's just for the Earth, I could imagine that as we discover more and more about other planets, we will come up with even more explanations or ways in which you could decouple the oxidation state of a mantle from what you might expect purely from the gross oxidation state of the planet.
Going back to this idea of looking at the core size and the mantle size as some sort of measure of oxidation state, how do you decouple that from the possibility that mantle has been stripped away in like hit and run collisions, so not due to any sort of thermodynamic process, but just a mechanical one?
So in that case, if you're doing it mechanically, you've no longer got a chemical equilibrium at that point. So then you're not necessarily looking at a record of oxidation state, you're looking at a record of impact. So mercury would be the obvious case for that, because we don't know whether the very extremely large core size of Mercury relative to its mantle, whether that's purely a function of its accretion distance from the sun, or due to late impacts. If one could have meteorites that access the composition of Mercury, we would be in a reasonably strong place to answer that question, because we should be able to see from a combination of elemental and isotopic measurements. We can predict for a certain core mass fraction and oxidation state, we can predict the distribution of metals. We should be able to see those if we had meteorites from Mercury. That's a big if. Or if we were worried about impact, we could even look for isotopic tracers of impacts of stable isotope fractionation. The big challenge with Mercury is we don't have any uncontested meteorite samples of its mantle.